Hey there, everyone. Thank you for coming to my talk today. My name is Jared Van Dam, and I'm presenting this paper on behalf of Alex Krasner and Dr. Joseph Gabbard. The title of our paper is called Drone-Based Augmented Reality Platform for Bridge Inspection, Effective ARQ Design on Visual Search Task. So the agenda for the presentation today is we'll start off with talking about current methods of inspection, issues with them, how they're done, and where we think that we can improve them, and then how drones and AR are currently used in bridge inspection, and then finally, how we think AR and drones can kind of help in that space and how in a better form they can do better for bridge inspections. Then we'll talk about the study design and the testbed that we created. So we created our own virtual bridge to kind of test out some of these topics in the lab. And then we'll talk about the results from this initial experiment, and then finally go into the take-home points and the future directions that we'll have for this research. So the background of this experiment and this kind of paper is that there are two kinds of bridge inspections. One is routine bridge inspections, which they have to happen every 2 years, and they don't require a very in-depth or kind of personal aspect like the in-depth inspections have, like you see here. So you can be standing on the roadway and looking at the bridge and use binoculars to look at the bridge. You don't have to be very close to it to do these inspections, but they do have to happen every 2 years, and you do have to look at all areas of the bridge. The other kind of inspection, though, is in-depth inspections, which require these snooper trucks. You can see this white arm here. This is a boom of the truck, and same here, the yellow arm here. These in-depth inspections require that you be in close contact with the bridge, like you see this person here in close contact, and they require that you get up close and look at every area of the bridge to kind of do a more detailed inspection of it and to look for different defects and note them in the inspection report. And our hope is that drones can be used in both of these spaces. Right now, the more likely scenario is that they'll be used simply for the routine bridge inspections because there's kind of a lower bar of quality for those. And at the moment, the drone platforms that we have don't have the same level of quality that you would get from having a physical person there within arm's reach of the bridge. But and maybe in the future, we have drones that can be used for both in-depth and routine inspections. So as mentioned earlier, there are some use cases where drones and AR are being used in bridge inspection. However, those uses are kind of light, if you will. They are usually, at least for drones, they're often used for model building and for image generation, but they are not really used for live inspection, which is what we're trying to do with our project. And it's what the bridge inspectors really wanted, was this live inspection tool that would allow them to fly a drone, have the drone fly itself up to the bridge, and then the inspector can make the inspection, can tell it to go different places and to look at different areas while they're there on the ground or in the office, but to have it be a live inspection tool. But drones are being used, but they're really just used to create these 3D models and to take pictures of problem areas. And one kind of reason for that is both the FAA and Department of Transportation have rules in place that don't make it impossible, make it harder to use these drones because, again, they're flying in populated areas and there are some regulations that prohibit that kind of use. So, and for future use, that may be something that a hurdle that you need to cross is getting the FAA and Department of Transportation behind the technology. In terms of AR, though, AR is being used in bridge inspections. This is an example of one company who has a smartphone app with a GPS on top of it that can show you the different parts of the bridge, and then I believe there's a tool in there that allows you to make notes for the different areas. So if there's a defect here on this area, you can make a note of it and it'll tag it in the software. However, these tools are not first-person view. They're kind of rudimentary and they don't allow you to have any kind of defect recognition. So if there was a defect here, like a crack in this spot here, the app wouldn't show you that. It wouldn't tell you that. It would just tell you that there's a piece of this bridge here. So there is AR and are drones being used in bridge inspections, but their use is kind of light at this point. I think there's a lot of area for improvement in that space. So going off that, what we think that AR and drones can offer in bridge inspection is a better way to access these hard to reach areas. So as we saw in the previous slide, there were that big span bridge with all the trusses on it, and that's difficult to get to. Even with the snooper trucks, it's hard to get into all those areas, but with a drone, it can just simply fly up there and take really good video, take good pictures of it, and give you that information back. So it also has computer vision defect detection. And so we can do these things like you see in this picture here, where we have the AI machine learning algorithms are showing the spot and saying this is a roller bearing, or maybe this is an area of spall down here, and the CVR algorithms can detect that and can show that to the operator. So even if the video that you're getting back isn't incredibly high quality, the defect detection on the CV can help that, can alleviate some of those stresses. And in addition to that, in addition to detecting defects, it can also help tag and inventory different things. So one part of the inspection reports is that you have to list all the different pieces and parts and then their condition for each one. And so the drone and the related CV algorithms can detect all these things like a roller bearing, and then also can generate the condition of that. So it can say it's good, it's poor, and add that to the inspection report. And that can all be done manually. The other thing that you can do is inspect and show the bridge over time. So if you have a 3D model of it that you had in maybe 2014, 2016, 2018, etc., you can show how, let's say, an area of spall, like you have here, how that area of spall has gotten bigger over time. And you can see maybe it's followed an exponential growth, maybe it's followed a linear growth, but you can see how that crack, that spall, is developing over time, which, based on the interviews that we had with the inspectors, that was really an invaluable tool, and that was something that they were really excited about being able to have in their inspection toolkit. So I think that would be a very good tool for them to have. You can also add helpful augmentations like we see here. This is showing an area of spall underneath the roadway. So if you were looking at this with a simple visual camera, you would see what looks like a basic roadway here. But with the thermal camera that we have, we can overlay that visual camera with this thermal camera, and we can see the areas of spall beneath the surface. And so typically, to find these areas, you have to do what's called sounding, where you drag a chain or you tap a hammer on these certain spots and you listen for the sound that it comes back. But with the thermal cameras, we can overlay this on top and we can see the areas of spall underneath. And so we can augment their vision with, these thermal cameras and help them out even more. Finally, by having stereo cameras on the drone and then a head-worn display, we can have better depth perception than you would get with a simple handheld device like we saw earlier. And so you would not only be able to see this area of spall, but you'd be able to see the depth associated with it. So how deep is that spalled area, and how bad is it based on the depth. So to answer these questions, we developed this test bed, and we did it in Unity 3D. And this test bed allows us to have a drone follow this track. So you can see the track here in white. And the drone will follow this path, and it follows it at a set rate rather. And so each run is only 2 minutes long. And so it's a time pressured task they have. And in these tasks, in these trials, they have to select these different areas of these different target areas. And the target areas are these dot patterns here that you see. And so they may be highlighted, they may not be, depending on the different target, but that's what they're kind of looking out for in the task. And so to come up with the different levels of saliency, we have 80% correct for the easy one. This was done with a pilot study that we did. So these are the easy ones here on the right side. And then the medium one here is this one that the corner bound augmentation is highlighting. Then the hardest one to detect is this one here, if you can see that one. And so in the pilot study, 80% got these correct, and then 60% of these were correctly identified, and then 30% of these were correctly identified. So that's how we came up with the levels of saliency for these defects, to have a easy, medium, and hard condition for the targets. And then in addition to that, we also have different kind of cue types. And so we have the bounding box cue here, we have the corner bound augmentation here, and then the outline cue here. And so each one has slightly different purpose to it, but we just added the different cues there. And so based on current CV algorithms and CV machine learning algorithms, we didn't want to make the system perfect. And so we have the system have a performance rate of about 50% hits. So 50% are like this, where it's correctly identifying the target area. 25% are false alarms, where let's say there's an augmentation here where it's highlighting something that is not a target. And then 25% are misses, where, like in this case, it's not highlighting something that is a target. And so in each trial, which was again 2 minutes long, there are about 40 targets per trial. And so it was time pressured, and the person was having to go fairly quickly through this to get all of the defects, all the targets. So the design that we came up with is a 4x3, where augmentation type is either control or none, bounding box, corner bound, or outline, by 3, saliency, low, medium, and high, like we saw earlier. And those were within subjects, and so they completed 12 total trials, each one being about 2 minutes. And after each one of these trials, they did a NASA TLX survey, as well as a shared situational awareness survey that measured trust as one of its components. So the results of the study, we'll go through them here. Overall signal detection was better in the augmented conditions. So you can see that here there's the bounding box and the corner bound were significantly better than the no outline condition here. And these are reporting the main effects here. User trust was also significantly higher with the outline type augmentation. And so just to note that trust is on a reverse coded scale. So 0 trust is considered the highest possible, and then 5 is considered the lowest. But the outline augmentation was significantly better from the no outline. And then the workload was the same, where participants had lower workload in the augmented conditions rather than the augmented ones, or non-augmented ones. And so this is again on the NASA TLX survey, so higher indicates more workload here. And this is based on not only the raw scores, but also the weighted scores, where participants rate the amount of mental workload required or physical workload required for the task. So as for practitioner advice and future work, while in our study the augmentations did not substantially help or hurt performance in the really easy conditions, we think that AR designers should limit the use of AR during easy tasks because it might lead to an overly cluttered display without substantially improving performance. This is backed up by prior research here. And in our study, the augmentations weren't very helpful in the really easy tasks and in the medium tasks as well. And so if you can kind of limit their use to more difficult to attack targets or limit their use entirely in these really easy tasks, you can create a less cluttered display without really improving performance much above the control conditions. And so in addition to that, the outline augmentation can be useful when you need to have users understand the exact shape of an object. So if you remember from one of the earlier slides, there's that picture of the bridge with a big area of spall in it. That's really important for the inspectors to know the exact area of that, the exact outline of that, to estimate the square footage of that defect. And so using the outline augmentation in that sense can be really helpful there, where they need to know the exact shape of that, the exact outline, where the target ends and the normal background begins. So that can be a good augmentation there. In addition, that outline augmentation also engendered more trust in the users. And so if you're a designer and want to increase trust in your users and you're using AR, the outline augmentation can be a good use of that. And so the next analysis that we're doing, we are focusing on the idea of proximal queuing. So it's queuing where the queue is next to another queue, like you have in this case, where the bounding box queue is next to the corner queue. How does that impact performance? And so in this scenario where it's next to another queued object, we don't think it'll impact performance all that much because both objects are queued, and so your attention will be drawn to both of those. However, in the situation over here to the right, where you have a queued target next to a non-queued target, we think that it might hurt performance because your attention is drawn to this queued target and you might skip over this one here. And that was something that we saw anecdotally in the research in this experiment. Was a lot of participants were saying that as they're going through it, they're simply going from queue to queue and not target to target. And so instead of looking at all the areas of the bridge, they're simply looking for the queues and not looking for the targets as well. And so we're kind of wondering if that happens, and if so, what the distance is for that to happen. So does it only happen when they're 3 feet away, or does it happen when they're 5 feet away? That's what we'll hope to figure out in this next analysis that we're doing. And then finally, we're also working on continuing to develop the guidelines for shared situational awareness, which is situational awareness for teams, basically. It's how teams of humans and machines or humans and humans, how they work together, how they transmit information. So we're working on design guidelines for that, as well as an assessment tool to quantify that. And so designers can also kind of rate their own displays on these metrics, and they can figure out if their design will enhance shared SA or it may limit it. So with that being said, I will open the door to questions.